Welcome back to part 2. Strictly speaking, the flame structures that we generate in part 1 are already sufficient if you are going to simulate pure combustion. However, since we are simulating carbon nanotube growth inside flames, the CNT growth region has to be incorporated within the flame structure. So to do that, we are going to need the growth rate model, but let me just back up a second. In this flame structure, what we see is there is a boundary of high CNT growth region, and those boundaries are determined by a certain threshold value that is implemented on the CNT length plot. I will show you in a bit how that works. Let's go back to the growth rate model. The name of the code is grm main flamelet.m. You will first need to input your CFD data. Again, the naming here follows that of the file that you have in the current folder. This code that is shown on the screen is actually a modified version of the previous tutorial. So the modified version includes the threshold specification at the bottom of the script. In this code, 70% maximum CNT length is actually the optimized value. You can use other values of the threshold, maybe 0.5 or 50%. It depends on the CFD data that you have. And this line is a horizontal line that corresponds to the threshold value. So we will see in a bit what that looks like. We'll just need to run this code. This will take a while, so I'll be right back. So the simulation is already completed. If you notice, there is a horizontal line here which represents the CNT high growth region threshold value. So this line is 70% of the maximum CNT length. Okay, so the length plot here has a maximum at around 15 micrometers. And the high CNT growth region actually lies between the two intercepts here and here. So you can expect your high CNT growth region to exist between those two intercepts. You can also figure out the maximum CNT length from the workspace. You have exactly 15.268 micrometers as the maximum CNT length, and if you take 70% of that value, you will have 10.687 micrometers. Now, how do you actually determine what the value of these intercepts are? What I normally do is insert two lines. The first one will be placed at the first intercept, and the second will be placed at the second intercept. So let's draw a straight line here, nice and straight. Adjust it a little bit. Let me copy that and paste. Okay, so the first intercept is easy. It occurs at roughly around 6.2 millimeters, but the second one is a little bit tricky. My way of doing it is to move the straight line to the previous tick and then dragging it using the cursor to the next tick. So let's drag it first to the previous tick, and let's count how many times we are going to hit our cursor button. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 31, 32, 33, 34. There are 34 small ticks between these two minor ticks. So if we have the intercept at the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, and 17th. So we have the intercept occurs at the 17th tick. So what we can do is a simple algebra. We have 34 ticks that represent a scale of 0.2. Alright, 7.8 until 8, we have this amount of cursor movements. And then for 17 cursor movements that represent the intercept, how much on the scale are we looking at? So we do a cross multiplication. 34 times x equals 0.2 times 17. And if you figure that out, that will be 0.1. So it's 0.1 from the first tick that we started from. So that's going to be 7.8, and then plus 0.1 here becomes 7.9. Now what you need to do is record those values of the intercepts 6.2 and 7.9 into the code for the flame structure. Let's scroll to the bottom section. Now you put those inputs here. In the left bound you would have 6.2, and for the right bound you would have 7.9. Now if you look at the next column here, we have the row for the left bound and the row for the right bound. So these rows represent the rows that are present in the radial distance data. If we look at the r_mm data at the rows that contain the values of 6.2 and 7.9, we will find that 6.2 exists in the 49th row, so we will write that down, 49, and 7.9 exists on the 62nd row. Alright, we will write that down also, 62nd row. These values are important because later on, when we are going to generate the flame structure in the mixture fraction space, we will need these numbers to obtain the left and right boundaries of the mixture fraction. We will look into that in a bit. For now, we will use the values of the left bound and the right bound of the CNT growth region into these two lines of the code. The left bound was again 6.2, so we will change that 6.2, and then the right boundary will be 7.9. If you happen to have a different range of temperature, for example maybe your CFD data that you have plotted is maybe 2000 Kelvin, then you can change this boundary. But for now, the data that I have has a temperature of 2600 maximum. Once you have plugged in these two values in line 58 and 59 respectively, then the high CNT growth region will be automatically plotted for you. Okay, so the lines, the boundary, and the shaded regions that you saw earlier will be plotted automatically.